All right, welcome everyone. My name is Yusuf Webby. I'm the climate science lead at ADIA Lab. It's a pleasure to be here today with of course, the three experts we'll hear from in this breakout session. So thanks for coming over. We have three incredible speakers today, so let's dive right in. And first of all, I'll introduce Dr. Adam Schlosser. He's the senior scientist and deputy director at MIT Center for Sustainability Science and Strategy. That's a lot of S's in one sentence.
We call it CS3 for sure.
So Dr. Schossel's work focuses on integrated modeling of natural, managed, and built systems to inform global sustainability strategies. Dr. Schossler has also undertaken studies of hydrology, weather, and climate and their predictability, as well as their limits to prediction. So today, we'll hear from him a little bit more on AI-driven modeling, the need for integrated high-resolution predictions, and how these methods can guide sustainable development. So over to you, Dr. Adam.
I should hold that too while I'm speaking, right? Okay. Thank you, Yusuf, and thank you to ADIA for this opportunity to attend. This is my first time here, and it's just been a very impressive session, and I'm just happy to be here. So today, what I'd like to do is kick things off by sharing with you thoughts that I have on AI and how it relates to our research. We will get slides just a minute. Okay. Yeah. Oh. Wonderful. There we go. Okay. So what I'd like to share with you today, and I think all of the speakers recognize that we are between you and lunch, and we're already behind schedule. So I'm going to try to make my comments short and sweet, and hopefully there'll be some questions that there'll be time for. But again, what I'd like to do is kind of go through some of the work that we're pursuing at our center, how we think about AI, and just exactly how far can we and should we actually really go with all of this. So briefly, the center that I sit at, it's known as, again, it's the Center for Sustainability Science and Strategy, CS3. You're going to hear me say CS3 a lot. It was formerly known as the Joint Program on the Science and Policy of Global Change. Longer name, but both of them essentially what they're trying to embrace is this issue of integrated modeling. Okay, so there's folks like myself and Bjorn Stevens, who you heard from in the plenary session. I sit very much on the climate weather side of the science equation, if you will. But our center, historically, has been comprised of scientists like myself, but also economists. And we think very broadly about how we take both of our approaches in predicting climate and weather, as well as predicting the socioeconomics of a growing society. How do we bring those all together to think about strategies and pathways that not just meet climate targets, and we've heard a lot about that this morning, and we've heard a lot about physical risks, but how we think about other challenges and other targets that we need to think about in a growing society. And that's really embraced in this issue of just sort of a coexisting, co-evolving world of changes. Can't just think about our planet as something that is just climate-centric. It's a growing, complex society. There's a lot of things that interact and feedback, and if there are two words that I want you to take with you from this slide to the rest of the talk is, again, these interactions, these feedbacks, not just between the physical systems, between the social and economic as well as physical systems, and how do we build a prediction system to think about all the plausible futures. That was another word that was talked about today, plausible futures, very much in our thinking. So this briefly describes our framework, and again, it is a very deliberate attempt to take much of the state-of-the-art in terms of modeling the climate and the physical systems that you saw this morning, but also linking together the socioeconomics of the problem, if you will, or of the challenge. So there's a lot of interaction, there's a lot of arrows that you see going between, again, our human system, our socioeconomic modeling system, to our physical system, to our Earth system modeling system. We employ models very similar to what you heard from Bjorn, which are EMICS, Earth Models of Intermediate Complexity. And that's sort of that larger box there that you see with the MIT Earth System model. But we link them to more detailed and sophisticated models that Bjorn also talked about. So that is really the challenge. All these arrows, all these linkages that you see between these models is sort of where a lot of our work is done. And in terms of AI, what hopefully I can touch upon in the slides that follow. This just gives you an example of the types of outputs that historically we've developed. So every 2 years or so, we put out what we call a global change outlook. We have one coming out this year in 2025. Literally, as I'm talking to you today, we're putting the final touches on it to release it. But this is the sort of output that we provide. So we think about sort of two major sort of pathways. One is current trends, which you see CT there, and that is sort of taking all of the current policies that we think are in play now or that we know are in play now and sort of extrapolate those into the future. And then we think about more aggressive emissions mitigation pathways, very much aligned with the sort of SSP pathways, again, that you saw this morning. And we've developed over the years a system to think about many different dimensions of uncertainty. And again, this speaks very much to the talks that Bjorn had touched upon, but not just in terms of the climate, but also in terms of the socioeconomics. So within every one of these trajectories, we have we simulate hundreds, if not thousands, of different tweaks or sort of configurations to an overall pathway, and we get these sort of bands of possible outcomes. And the bottom line is that this is a global projection that you see here. The challenge is what does it actually really mean to people, and what do we really need to do? What do we need to think about in terms of not just mitigation, but adaptation, and also the willingness to do that. So again, this really sort of brings out, I would say, several major items to think about when we think about sort of opportunities or challenges for AI. Coupling, linkages, feedbacks. You see a lot of arrows, a lot of circular sorts of mechanisms. Scientists, researchers, we love circles, it seems like. So there's a lot of arrows here, and these arrows are really to highlight or emphasize the fact that this is a very connected system, a very complex system, not just within the climate and the Earth system, but with that and coupled to socioeconomics. And how does that all come together, and how do we think about the future? So there's a lot of challenges when we think about these feedbacks and linkages. Within each one of these model components, there are process level understandings. There's critical capacities that we need to build a better understanding and to build a better appreciation for in terms of what we actually need for these predictions. And at the end of the day, when we think about AI, it all comes down to data. It all comes down to observations. What do we train these AI methods on? There's a lot of talk this morning about model consensus, and that's really important, but it's also important to realize that consensus doesn't necessarily mean that the models are right. It doesn't necessarily mean because the models are right now that they're going to be right in the future. So how do we think about all those challenges? On top of all that, there's just the fact that we have people within this system, and that was actually another topic that was brought up in the plenary sessions this morning, and it really does pertain very much, or there's a very, very strong underpinning to what we model in all this. We kind of forget that we're modeling people, and as we strive to get these models down to greater and greater detail, right, the differences and disparities, the landscapes of all of that are going to become more and more important. There's going to be unintended consequences, hidden consequences. There's going to be coexisting, co-evolving changes. How do we know that they're there? How do we actually observe them? And when we do observe them, how do we train our AI models to encapsulate all that? This next slide is to literally just give you an appreciation for how we build the models. And a lot of what you see on the left here is what, again, I have the benefit of our plenary speaker who talked a lot about how we build Earth system models. But on the right side, it's really about how we view the socioeconomics, the natural, not just the natural systems, the managed systems, the built environments. How does the economy support all of that, and how do we weave that into our Earth system model? There's a lot of linkages there. It's not just emissions. We talked a lot about emissions this morning. There's a lot of other connections in there that we have to think about. And the same rule that Bjorn had applied earlier applies here. As you put more and more detail into these models, the computational expense gets very large, and it grows nonlinear, even more nonlinear than what Bjorn had talked about this morning. So how do we think about implementing methods that make that more efficient and allow us to think about more and more plausible futures in our forecasts? Because we need that to build probabilistic forecasts. So I think all of you have probably heard of the 70-30 rule when it comes to AI. And I always don't like it when a speaker asks this question, but I am going to ask it anyways and ask people in the room here, how many people have heard of the 70-30 rule? Oh, not that many. Good. Okay. So basically the 70-30 rule when it comes to AI essentially says that if you have a model system and you want to use AI, the idea here is that you only use about 70% of AI to exercise your model. And the last 30% should be human intuition, human interpretation, our own expertise that gets sort of factored into that. You could also apply that too to just in terms of the models themselves. You can think about maybe 30% of the models are more process-based, actually explicitly model that rather than using AI to emulate them or mimic them, if you will. What's interesting is that even when you think about when you read more into the 70-30 rule, it sometimes actually even gets flipped. So in some situations for modeling these types of things, it's not 70-30 to AI, it's actually 30-70. So only about 30% of the AI actually gets in there, and the rest is explicit modeling. But the idea is that if you have these integrated models, again, we're combining Earth system models, these physical models that you heard a lot about this morning, with more of sort of the economic models themselves, you have this sort of utopia where you might be able to, at some point, understand which elements of those model components could actually just be driven by AI and improve your efficiency, and which ones still have to sort of be more complex, have to be more explicit in their representation. And again, there's still arrows here. You still have to understand where the connections are, where the critical capacities for the models themselves, and what linkages are important. And all those questions are listed here at the bottom, these important underpinning questions. What are all the connections? Can we even observe them? How do we identify them when the data is available? So just to unpack this a little bit, there was a study by Claudia Tibaldi, who works with us in our team quite a bit. And what she did is to sort of put together a schematic of what perhaps maybe one of that sort of utopian view of integrated modeling could be. And you can think about sort of the conceptual framework of this, where you have, again, these explicit representations of all the Earth system components that you need, coupled with, again, these managed sort of built environment systems that include socioeconomics, include all the impacts, and all that's done explicitly, computationally expensive. In an augmented framework, you've actually begun to identify which one of those elements could be replaced by AI efficient emulators to speed the whole process up. So a lot of challenges there. Again, you're probably going to sound like a broken record, but obviously, which components we're actually going to replace, it's not very clear which ones those are right now. Are they doable, and how are we going to do that? There was a lot of, in Claudia Tibaldi's paper, she talks a lot about impact-relevant climate outcomes. Typically, these are extreme events. Right? The extreme events are the ones that really have the impact punch. Unfortunately, those are the ones that don't occur very often, so they're not observed very well, and we also know that these are changing. So that actually inserts a bit of a complex issue here, where if we don't have the observation sufficient enough to actually measure and identify these extreme events, how do we know that we've captured them in AI and emulator methods? Again, there's additional challenges with scale, not just in terms of the details, but even just the inconsistencies of scales across all of these models. And ultimately, we want to think about all of this at a local scale. And that, again, brings back the computational expense. One thing hopefully we'll get into in the slides that follows is that in this particular exercise, they really just thought about the biogeophysical impacts, which are things like you heard about this morning, water impacts, energy impacts, and the like. But within the Earth system, and there's a growing recognition that biogeochemistry, and not just biogeochemistry itself, the interactions of biogeochemistry with biogeophysical systems and the socioeconomic systems is becoming more and more important and more aware in the models that we build. So with that, what I'd like to do is just to use the rest of my time to just go over a few sort of perspectives of all these issues that I've laid out. The first is just thinking about the feedbacks within the natural system. And so I come from a very land climate-centric way of thinking about this. And 20 years ago, one of the hot topics was how strong does the land and the climate system interact? And I just recently went to a colleague's webpage who has now a list of all these metrics that try to identify how strong that coupling is and how we measure it. And the list there is about 10 times larger than what I remember it. So it seems right now that the science is actually moving towards a far more complicated picture than it once was. And the only reason I bring that up is that just in terms of AI and its promise or its prospect to addressing these sorts of things, looks like it's becoming more and more, or less and less tractable an issue, unless we really are able to identify which one of these metrics truly capture what is the strength, and we have the observations to support that. So again, this goes back to the feedback, the linkages. Similarly for land transitions, for land use. Land use change not only has an important impact on climate, but the decisions that we make about how we utilize land resources is very much tied to socioeconomics and tied to non-climate targets, such as biodiversity. We've done a lot of work looking at how we take our economic model that projects land use change and downscales it and tries to reconcile not just climate relevant targets, but also biodiversity relevant targets. And what are the impacts of thinking about each of those separately and together? What is difficult to appreciate, at least in this slide, and I think these slides will be shared with everyone, is that details matter. The downscaling methods that you use and the choices that you make between whether or not thinking about one target or two targets, those issues really matter when we think about using AI to downscale all of that. And again, go back to other keywords. The devil is in the details. To touch briefly on biogeochemistry, work that we're doing to look at hydrogen. So hydrogen obviously has a big role in terms of energy transitions. It's probably one of the more promising replacement fuels for a decarbonisation strategy. But as it turns out, when we think about this in terms of the natural system, there are not only biogeochemical implications for that, but the biogeophysical processes that affect the biogeochemistry are all intertwined. So hydrogen is not a direct greenhouse gas, but it imposes an indirect effect by affecting the lifetime of methane due to its chemical interactions in the atmosphere. But it turns out that the largest consumption of hydrogen is in the soil, and it's in a very thin layer of the soil. And a lot of the work that we've done is to use process-based models to try to estimate how much consumption of hydrogen in the soil will play out under altered climates. The point I want to make here for AI is that the models that we use are process-based, because the only sources of information that we have, observations that we have, are from these 4 sites that you see on this slide. So there are very few sites in the world that actually measure hydrogen, or at least the consumption, or what we call the deposition rates of hydrogen. So we're really tied to using process-based models right now. And the prospects of AI, at least in this space, are very much a challenge. Quickly transitioning from hydrogen to water, which is there's a little bit more of an encouraging prospect here in that we've measured water a lot. But what I'd like to just sort of point out here to tie in is that to date, a lot of the focus has been on just the availability of water. But again, I think as what was touched on in this morning's plenary sessions, the quality of water, the impacts that we make on land management, fertilization, any sort of other contaminants, point source contaminations. The quality of water, which brings back the biogeochemistry feature, is very much important, very much tied into providing projections of fresh water. And what we find is that there's no real direct relationship right now, and our observations in terms of the linkages and the feedbacks between these systems are limited. So in terms of AI, we have a ways to go. All hope is not lost, though. In terms of that framework, what we do find is methods like generative AI can help us, at least in terms of providing things like precipitation, downscale precipitation, which is clearly a big driver in all of this. So there are certainly, I would say, more than encouraging prospects for maybe not addressing the 70-30, but the 30-70 when it comes to that AI and explicit process-based mix. Shifting gears a little bit and thinking again about the connections between human systems and Earth systems, work that we've done as well that sort of holds promise for having AI factor into all of this is thinking about extreme events. We've done some work looking at maximum temperature. Again, temperature is a variable that we observe quite a bit. And what we find here is that by using these sorts of AI ML methods, we can take the global projections of temperatures, which I've shown you earlier, and bring them down to local scales and provide a metric that has a little bit more of an impact punch. So what you're looking at here are projections of extreme temperature at a local scale that are actually derived from our global temperature outlooks. This work here was motivated by the fact that not only extreme temperature affect humans, but extreme temperature also affect infrastructure and energy systems. Extreme temperatures can affect power transformers, other aspects of infrastructure. And so the promise is that we can use these methods to get at those impact metrics. There's a little bit more to unpack there, but due to time, I'm gonna move on. I'm gonna skip this for now. I'm not sure how I'm doing on time, Youssef, but I'm gonna skip that and just simply leave you with the fact that there are also methods that we use that are based on triaging. Rather than using explicit models, you can just use data and simply design metrics that give you a hotspot analysis, whereby you can not just look at physical impact metrics, but also just look at socio-demographics and socioeconomic effects and take sort of two landscapes and combine them together to give you a hotspot of where you can focus your attention on, again, these sorts of more computationally expensive yet possibly some AI enhanced and augmented approaches. So with that, I think I'll stop here. Again, in the interest of time, I'm not going to go through each one of those bullets, and maybe we can cover them in the questions or later on. So thank you.
Thank you, Adam. I think we have time for about two quick questions, if anybody has one.
Good morning. My name is Nicholas Gilani. I'm a founder of an ag tech company here in Sharjah, northwest of here. We have succeeded in converting soil, desert soil, as well as depleted soil using AI and microbial elements. And what you have done here, I think, should you ever want to come to the UAE, you'll find a very ample audience to exchange information, for example, our company or the government about would that be. You'll get a lot of data points if you have the AI, and the results, I have no doubt, will be of much use to you.
Thank you for bringing that up. And one item in all of this that I couldn't bring up just in the interest of time is, to your point, the lack of data and the lack of open data. But to what you've described, our lab have relationships with certain industrial companies where we can get that proprietary data, as you say, that really kind of advance the science. So this is the exact sort of I think, relationships that we need to build between the scientific community and private industry. So I'm very much aligned and resonate with that thinking. So thank you.
Hey, just a quick question on, I guess AI is all the rage at the moment. I know there's operational models out there from governments that you get your typical numerical predictions. How are the AI models that they're releasing competing with those traditional models? Are you seeing a change, and is it becoming a more accurate forecast with the AI models?
So I think there's a distinction here between, I think you're referring to the models that maybe Bjorn had talked about this morning, so the operational weather forecasting models.
Yes, that's correct.
So the models that we employ within our framework, certainly at a process level, use the same types of equations, if you will, as weather models. But we use them in a fundamentally different way, in such that we're not thinking about the deterministic forecasting. So I think Bjorn sort of pointed out this sort of deterministic and probabilistic sort of regimes of prediction. It's important to understand that for a lot of I think the promise that you see in AI emulator-based models in terms of prediction, it's that deterministic regime. So there's a cause, there's a very clear cause to a very clear effect. So in other words, you're going to see rain 2 days from now because there's a system a few hundred kilometers to your west and it's going to propagate and it's going to hit you. We think very much longer term, which is where we get into probabilistics. In other words, we might see that there's a change in precept 20 years from now, but it could be because of a host of very different factors that give you the same result. Those sorts of emulated methods, I think there's still a long way to go in understanding whether or not they are telling us what we need to know, simply because there are feedbacks. If an AI or an emulator is being tuned on a model that has the wrong feedbacks, you might get the right answer for the wrong reasons, if that makes sense.
Sure does. Thank you.